Hello, hello. Let's wait for a while. We have 13 students, 14 students. Okay. So probably we start at 5 minutes after 2. Okay. So far we have 13 students joined. Let's wait for another 1 minute. Okay. See if more students join in the group. Let's see. Hi everybody. Today is our fourth lecture. Okay. And we continues on the discussion of the shear strength of the soil. Okay. Now, last week we discussed that shear strength of the soil, the basic stress strain behavior. Okay, it depends on the density for dense sand, for sand, granular material, sand, and gravel, that kind of granular material. Then we classify as a dense material or loose material because the stressing behavior is they're different. And then for clay, fine grained soil, cohesive soil like clay, silty clay, and that kind of material, then we classify the material as normally consolidated or over consolidated because the stressing response also are different. Okay, so last week we somehow talked to there, and this week we'll continue to discuss the important aspect of the shear strength of the soil. Okay, like when we design a foundation or when we design a slope, uh, basically all of the earth structure, we need to know how strong is the soil, how strong is our geotechnical material, which including the soil, the rock. Okay, because we need this geotechnical material, the earth material to support your buildings, your foundations, okay, to support your road, to support your beach, to support any underground excavation, and to support the slope. Otherwise, we could have failure. Okay, we could have bearing capacity failure for the building, or the pile foundation, the deep foundation may be failed. The slope with slide down, landslide. We have the foundation. If we don't design properly, then our embankment, our road will have too much settlement and may eventually lead to failure. Okay, so before we need to know how to design this earth structure, we one important parameter we need to know is the shear strength of the soil. Okay, so that's why we today we will discuss what is it and how to determine it. Okay. Uh, Actually, I can start the recording. Let me record it. Okay. Okay. Now, when we want to understand the strength of the soil, uh, in fact, soil are far more complicated material than the other civil engineering material. It's far more complicated than structural steel, far more complicated than concrete, for example. Okay, so what we are learning in undergraduate in year three soil mechanics, basically we will use a simplified soil model because the soil itself, the stress strain characteristic, is difficult to predict. to be honest. So we have to use some simplified soil model, okay, and which is turned into the Coulomb's uh, soil model, or the currently we are using is more Coulomb failure criteria, okay, which is named after Professor Moore and Professor Coulomb. They developed this model, I think, more than how many years? Close to 100 years, almost 100 years ago. Okay, but we're still using it because it's one of the most simple and easy to understand soil models. Okay, so basically, all undergraduate civil engineer students have to learn more Coulomb failure criteria to model the soil strength of the soil. Okay, but of course, when you go to more advanced study, then you know that more Coulomb failure criteria is basically quite too simple. Okay, we may have to use a more sophisticated soil model. Okay, basically we will use the more Coulomb failure criteria to help us to interpret the shear strength of the soil. Okay, basically soil not like concrete. Concrete is a bonded material. Okay, all the particle uh, of the concrete material, that means the fine aggregate and the coarse aggregate of the concrete, are bonded together by cement paste, the hardened cement paste. Okay, so it's 100% bonded material. For steel, again, it's a bonded material because it's bonded by the atomic, it's by through the atomic bonding of the iron molecule. Okay, to bond the steel together, and then we have also have some uh, carbon in the middle. Has a is a if you remember, it's called uh, is by intertextual substitution, so to strengthen the bonding of the carbon to carbon atomic bond, okay, to make the stainless the steel, okay, carbon steel, okay. So um, the common type of civil engineering construction material, no matter it's concrete or structural steel or aluminum, okay, most of the strings come from the bond string. The the particle are bound together through either through physical natures or through chemical nature. Okay, but soil is not, it's a non-bonded material. Okay, soil, they are basically all soil, no matter granular soil or a cohesive soil. They are non-bonded. They are not. The string is not come from bonding, but the string is come from shear. It's rely on the shear. In other words, it's friction. Okay, because soil is individual soil particles. Okay, so if we don't have confining pressure, okay, no pressure apply into it, soil is basically very loose. It doesn't have much strength. Okay, but when it's subject to stresses, then the particle in between the particle and particle, the interface of the soil particle with another soil particle, we're able to mobilize the frictional resistance between particle surface, and this frictional resistance will therefore tend to become shear strength. Okay, so it's not bonded. Okay, it's not a concrete. You have the cement paste bonded together. Even though there's no confining pressure, okay, you have a whole block of cement standing alone. whole chunk of structural steel standing alone, no problem. Still very, very strong. Okay. But from sand, if you don't have the confining pressure on the outside, basically it's just uh, a pile of loose sand, a pile of loose particles. It's not strong, very, very weak. Okay. But when you have pressure applying to it, then this pressure will mobilize the surface friction, the friction between the soil particle from the surface of soil particle to the next particle. And through this frictional resistance, then it generates a shear resistance, the shear strength. And that's how soil able to mobilize the strength of the soil particles. Okay, so it's not bonded material; it's a shear strength material. Everything is come from shear. That's mean frictional resistance. Okay, so that is the difference between soil and the other type of civil engineering material. Just to define some of the important concept. Okay, as I mentioned before, soil is come from the shear strength. Okay, the shear strength is actually in a more definition wise. Okay, is the maximum internal resistance to the applied shear force. Okay, that means if we have some soil particles here. Okay, this is a soil particle, imagine. Okay, so we have the external applied stress, this major principal stress in here, major vertical stress in the vertical direction, and minor principal stress in the horizontal direction, minor principal stress in the horizontal direction. Basically, it will feel mobilize a potential failure plane. Okay, this is shear plane. Okay, in this shear planes, actually what is going on is mobilizing the shear resistance. Okay, here is the shear resistance that develop along this potential failure plane. Okay, so this is the shear stress that would shear is coming in a couple. Okay, have to become in a pair. One, they have to be balanced. Okay, so if we have a shear going to the right, then on the other side of the failure surface, you have the shear stress to the left. Okay, I put a N stand for on the failure plane. I put a F stand for failure plane. Okay, but actually, perpendicular to the shear stress, we also have the normal stress develop. Okay, basically along this failure plane. Okay, the soil is trying to shear by friction, frictional resistance. Okay, and if the stress is strong enough to overcome this friction, then the soil particle will slip apart, Okay, how strong is the soil is dependent on how strong is the frictional resistance between one side of the soil particle on one side of the failure plane and the soil frictional resistance of the soil particle on the other side of the failure plane. So, in order to mobilize the shear, you learn friction through your physics, right? You have to have a normal stress. Now, this normal stress perpendicular to the potential failure plane is basically come from the confining stress. When the confining stress, stress is developed everywhere. Okay, so you can reorient the stress. Okay, so from the principal stress location, we can rearrange to the failure location, failure plane location, and we find out the resultant normal stress after stress rotation, and what is the normal stress potentially applied perpendicular. Perpendicular. This is the failure plane. This is the normal stress perpendicular to the potential failure plane. And from that, it's able to mobilize the shear resistance along this failure plane. Okay, just like this shear resistance is mobilized by this normal stress on the lower shear plane. On the other hand, the upper shear resistance equal but opposite to the lower shear resistance will be mobilized on the upper part of the shear plane, which is also so the normal stress on the lower and upper part of the failure plane is the same, okay, equal but opposite, and then the shear stress across the potential failure plane is also the same magnitude but opposite direction because it's just action and reaction. Okay, so shear strength is this through this uh, is a shear resistance developed along the soil particle, which is the maximum internal resistance to the applied shear force. Okay, and the more complicated thing associated with the shear strength of the soil is everything will depend on the drainage condition of the soil. Okay, if it's undrained soil, that means the drainage is very slow, or we don't allow the pore water pressure to dissipate, then the thrusting response is one thing. But if we allow the excess pore pressure to dissipate, okay, then the thrusting response is another thing. So the complexity of soil mechanics is first, it's not bonded material. It's a frictional material. Everything is mobilized by the internal friction of the soil particle. So this is one thing different than the concrete or the other civil engineering material, steel, for example. And the second in here, it also depends on the drainage condition. Okay, uh, it could be drained or it could be undrained. Okay, so when we want to understand the shear strength of material, first we have to ask, is it a granular material? Because the frictional resistant granular material is different. So granular material does mean it's sand, gravel, or sand, seal, gravel. Anyway, the major components of the soil is sand. Okay, so make it more granular material or cohesive material. That means clay. Clay is the predominant cohesive material. Granular material, sand is the predominant material. Okay, so first of all, we need to know, is it granular material or cohesive material? And second thing, we have to ask, is it drained? What is the drainage condition? Is it drained or is it undrained? How far is the loading in compared to the dissipation of pore pressure? Okay, if the loading is applied fast, then the excess pore pressure doesn't have chance to dissipate, then we call it undrained condition. That means the excess pore pressure will not have chance to dissipate. It will stay in the soil matrix. Okay, so the pore water will play an important part in the development of shear strength across the interface, the frictional interface. Okay, you can imagine that if you have some water along the frictional interface. Water will act as a lubricating effect. Okay, so you will reduce the potential frictional resistance. While if all the water drain away, okay, then the frictional resistance will just rely on the interlocking property, the frictional property of the soil particle on the two sides of the failure plane. So it doesn't have water. So theoretically, the frictional resistance will be higher. Okay. So because of that, we need to know how's the groundwater, the water in the soil particle will play an important role in determining the shear strength. Okay. So when we're talking about determining the shear strength of the soil, first we need to know, is it granular material or is it cohesive material? So you have to pick out these two important as different first. Because they are different, they will result in highly different behavior. Okay, and then by after we know that what kind of soil is granular soil or is a cohesive soil, then the second question we have to ask, is it drained? That means pore water pressure can free to move away from the soil particles. So it's a drained. Water can freely drain away from the soil particle during shear. Or undrained. That means water, the permeability of the soil is very low. So water is difficult to escape away from the soil particle during shearing. The pore water is still staying in the pore, not able to dissipate away from the potential failure plane. Okay, so it will stay in there, and because of that, the pore pressure will become an important factor affecting the development of the string. Okay, so then you can immediately imagine the complexity of just defining the string of the soil. Now, as I mentioned before, a lot of students they're quite afraid of the geotechnical and soil mechanics because in concrete, if you ask you what is the strength of the concrete, oh, this is grade 30 concrete, then you know that the nominal strength will be 30 MPa. Okay. Oh, this is grade 50 concrete, then you know that our design nominal strength is 50 MPa. Okay. And we know that this structural steel is grade 500, then we immediately know the yield strength of the steel. We design strength of the steel is 500 GPa. Okay, and for this grade of the high strength steel is 600 grade 600 steel. Then we know that the design strength is 600 GPa. So there's no uncertainty in that. But if I ask you for the soil, okay, what is the strength of this soil, okay, in your site, then you have to ask back, well, I have to do a site investigation, find out first what kind of soil that is. Is it granular material or is it cohesive material? Because the strength behavior would be different, totally different. Then I have to ask, how do you construct the building? How fast is your loading? Okay, compared to the permeability of the soil to determine is the soil under loading, is under drained condition. The pore pressure has the chance to dissipate away from the soil particle during loading, or undrained condition. That means the loading is applied compared to dissipation of pore pressure is relatively fast. Okay, or in other words, the dissipation of pore pressure in response to the loading is very slow, like consolidation of cohesive soil. When you apply the load, the excess pore pressure will take years. Remember, the consolidation takes years to complete. Okay, tens of years, 20 of years to complete. The the pore water pressure take long time to dissipate. So when we apply the load on top of the sample of soil, immediately what we can mobilize is only the undrained shear string, because at that time the pore water doesn't have the time to dissipate. So the pore water will still sit in the pore space of the soil particles, and because of that, affecting the development of the interface shear strength, the frictional shear strength. So the drainage condition is extremely important. Okay, so that's the difficulty of soil mechanics, is we need to know what kind of soil, what kind of drainage condition, what is the speed of the loading, so that we can design it's a drain the case or undrain the case. Sometimes a drain the case will govern the design. Sometimes undrain the case will govern the design. So we have to test using case, okay, to make sure which one is more critical, and we design with the most critical condition. Okay, so we have to do a lot of testing because we don't know the existing condition, and we have to assume it's drained. Then we do one set of calculation. Assume it's undrained. We do another set of calculation, and then from that we pick out the most critical one, and then use that as your governing design criteria, and then work out the factor of safety and things like that. Okay, so it's a more complicated in a sense. Okay, now let's continue to go. Of course, no matter how complicated, we always find way to simplify it for undergraduate learning. Okay, so that you can make our students easier to understand. Okay, originally over 100 years ago, Professor Coulomb, okay, like the Coulomb is the guy that developed the you heard of the name when you study physics, okay? When we talk about fiction, okay, you heard of the name Coulomb. It's the same Professor Coulomb developed this concept over 100 years ago. But anyway, he applied to the soil. What he's saying here is soil is a particular granular material. Basically, we have a so-called potential slip plane. Okay, when a soil want to fail, it will fail at a particular slip plane. Like remember Professor Coulomb in fiction, you learn in physics. Okay, if we have a block of object, okay, and then this is the shear plane, okay, we apply a normal force into it, okay, and then here we push the particle with a pushing force. Then what is mobilize the resistance is the shear that develop along the interface between this block of object uh, at what normal stress, then how much shear resistance we're able to generate. Okay, that is the physics that Professor Coulomb mentioned over 100, almost 150 years ago. Okay, so he applied this concept in the soil particle and find out that, well, soil particle is different than the solid object along the shear interface. Okay, soil particle, if we, it's like that. Okay, it's soil particle. Now, if we have a normal force applied to the soil particle along a potential failure plane, but the potential failure plane is not totally straight line. Okay, it's along the, it's a line, but roughly along the soil particles. Okay, because the soil particles are very strong, made of a majority phosphorus. Okay, silicon dioxide. They are very strong material. So our shear force is not able to break, okay, separate the soil particle itself. But that the shear force is only strong enough to make soil to move across each other. from particle to particle. If we have enough shear force, the particle just roll over each other and slip across each other. It's not it's not a bonding, like not a particle bonded to like a glue the particle glue together, bond together, and then if you want to shear, you have to break through this glue along the interface and fail it. It's not like that. Okay, is soil particles and other soil particle full friction. Okay, so if the shear string is large enough, it causes one soil particle to able to roll over another soil particle and then move along each other. So there's no breakage, okay? No damage on the interface material. No, it's just friction, okay? Friction is strong enough cause for the particle to able to roll over each other and then slide across each other, okay? Just because they are granular, they're individual particles. Okay, so when you apply the shear strength is large enough, it's just able to rotate, get over each other, and start to move. Okay, that's very little damage to the molecule of the soil particle. It's just the surface. Okay, the frictional surface may be with high enough of shear stress, causing the particle able to slip across each other and move, and that's become failure. Okay, so when this particle start to uh, able to move across each other, then we will develop this called this slip plane. It's not failure plane. It's a slip plane here. We call it potential slip plane. Potential slip plane. Okay, that means there's a soil particle and soil particle will be slip, roll over, move across this potential plane, and then allowing the soil particle to shear. Okay, that's not breakage. It's not bond separation of the material. Okay, because there's no bonding in soil. Basically, it's everything is majority of them is full friction. Okay, so basically, if your shear stress is strong enough, it just cause the material to overcome the friction along the potential slip plane, and then the particles just to slide, soil particles just slide across each other. Okay, and then the soil move, and then after that the soil fail. Okay, so the contact of the one soil particle with the another soil particle is through this very tiny micro slip plane. Okay, if we look at one soil particle, it's just this tiny slip plane. But of course, in a soil mass, there's many soil particles, thousand and thousand and thousand soil particles. So all this small micro slip plane join together become the potential slip plane. Okay, so and then that will be the failure plane of your soil mass. Okay, but if you look at the soil particle, it's just individual micro slip plane. But this micro slip plane just join together for all the soil particle along all the soil mass to form your potential slip plane of your earth structure. Okay, just like now, let me clear this. Okay, for example, if this is slope, this is a slope. Okay, potentially we could have potential slip plane here. Okay, like if we didn't design correctly our slope, this slope, maybe after heavy rainfall, we have heavy rainfall after the rain. then the rainwater go inside, okay, making this part of the soil fully saturated with this part of the soil mass fully saturated with rainwater, okay, and become very heavy. And because of the gravitational effect, then the soil mass want to slide downward, okay, because it has the weight of the soil and the weight of the rainwater all saturated in the void space of the soil. Now everything has to rely on the shear resistance of the soil developed along this potential slip plane. This is your potential slip plane. Just an example, okay. To a point, if the rainwater is heavy enough and the soil is heavy enough, so the driving force or driving shear stress is higher than the shear resistance developed along this potential slip plane, then this part of the soil mass would slide down, okay, collapse down. Then we have slope failure, landslide. 即係山泥傾瀉啦。Okay, basically, it's the driving shear force along this potential failure plane is higher than the frictional resistance of the soil particle across this potential slip plane. Then the soil will start to fail across this circular surface, and this is the so-called potential slip plane. Okay, the soil will fail along there, and this chunk of the soil will fall down in here. And if this is a road, there's some car vehicle passing by, then this soil mass may come and then cover maybe pedestrian or maybe the car, and then people in the car maybe get severely injured or killed by the landslide. Okay, so landslide is an example saying that along this potential failure plane, the mobilized shear shear force generated along a moving soil mass is larger than the available shear strength. Okay, so the soil along this potential failure plane is no longer able to support it, then the entire mass of this soil falling down, and we have landslide. So that is an example of it. Of course, when we do go into foundation and everything is similar concept. Okay, so we don't know where is this potential failure plane. Okay, that's why we have to keep testing. Okay, to see. We don't know where, we don't know when. Okay, so the only thing is here, for try and error, we test what is the potential of this failure. Will it or will it develop or will it not develop? We don't know. Okay, we have to try and to find it out. And where is this failure plane? We don't know. Again, we have to try until we find the most critical one. Okay, that means that the one with the lowest factor of safety, or with factor of safety less than 1. Okay, so that means that the soil is not able to support the load, and then the whole thing will slip. Okay, so basically that is the soil, how soil able to do resistance is for this interparticular shear resistance developed in between a little soil particle. Between them, we have a normal stress applying across the soil particle, and shear force, the shear resistance develop a core step. How strong is this shear force? Okay, if the shear force is greater than the shear frictional resistance mobilized by the soil, then the soil will fail, and it will slide, will fail and cause this potential slip plane. And the soil particle, this particle will move there, this soil particle will move there, then this soil across this interface would be failed. Okay, so it's all the micro resistance of each individual soil particle add up together, thousands and thousands of this micro particle, this micro failure plane, add up together, become the entire shear strength of the soil mass across the entire potential slip plane. Okay, so original concept is quite complicated. Then, of course, we engineer, especially under undergraduate, then we have to simplify this concept. And that's why we develop this more Coulomb model, or later we further develop it into more Coulomb failure criteria. Okay. So in this more Coulomb failure criteria, what we do is the soil is a soil model to idealize. It's not true, but just simplify it in an idealized way, okay, to represent the soil, to allow us to understand the response to the loading, okay. So make it simple, idealize the situation so that we know how a soil would respond to the external forces, the normal forces and the shear force, and then under what condition, then the soil will start to fail across this slip plane. Okay, there's two simple models that majority of undergraduate students would learn. One is an older one, is the Coulomb model, which is developed almost 150 years ago. But then we find it is sometimes it's not too suitable, especially when we have cohesive soil. And later we will develop the Moore Coulomb. Moore is named after Professor Moore. Moore circle is the same person, Professor Moore, and Coulomb is Professor Coulomb from England. Okay, from Oxford University. Oxford University. Okay, and combining these two researchers, this famous professor, then we do. Then people develop the so-called Moore Coulomb failure criteria. It's the most common soil model, simplify the soil model. I have to say that they are simplified soil model. The most common simplified soil model is Moore Coulomb failure criteria. Okay. When you go into a postgraduate study or you using some advanced geotechnical software, then a lot of it saying that Moore Coulomb failure criteria is too simple, is not truly able to represent the soil behavior. Then we have to use more and more advanced soil modeling. Okay, but for undergraduate, we learn Moore Coulomb failure criteria. Okay. Now, what is Moore Coulomb failure criteria? Okay, so basically, what we are saying here. Now, imagine soil is an element. Soil element. We take a soil element out. Just like you're in mechanics of material. Okay, we take an element out of your structure. Okay, here we take a soil element out of your structure. Okay, that we want to analyze. Okay, and then we cut it as, for simplicity, we cut it a square element. So turn out to be, okay, we may have a principal stress in one. Anyway, the stress is effective stress. Okay, principal effective stress applying in one direction, for example, in the vertical direction, and minor principal stress, minor principal effective stress, sigma 3 on the other direction, minor principal effective stress on the sigma on the other side. So you have major principal stress applying in the vertical direction, minor principal stress applying in the horizontal direction into a soil element. Major principal stress apply vertically, minor principal stress apply horizontally. It's all effective stress, okay? Because it is soil. So we assume the soil actually filled by the soil particle is the effective stress, not the total stress. Okay? So it's the effective stress applied in the vertical direction is a major principal effective stress. The principal stress applied to the horizontal direction is the minor principal effective stress. Okay, sigma 3 dash, sigma 1 dash, sigma 3 dash. Okay. Now, when we have major principal stress applying vertical and horizontal direction, then by stress decomposition, we know that the maximum location of the normal stress and then the shear stress is not in vertical or horizontal direction. It's like in a potential failure plane. Okay. Later we will tell you how to find this potential failure plane, or we can either call it potential failure plane. More correctly, we call it potential failure plane than failure plane, because failure plane give it a feeling that the failure will definitely develop in here, but which is not totally true. Okay, because in geotechnical, what we are finding is something that is potentially happen. Okay, so it's not exactly happen at that plane, because as I mentioned before, the actual failure is all the microstructure, all the soil grain, they fail across this microstructure and then join together into a continuous failure plane. Okay, so it's not truly a straight line. It's the failure plane. It's just if you magnify it, it's along the soil particle. It's many failure connect in between the little slip plane across the soil particle, and then in total it turn into a failure plane. The soil fail along there. Okay, so it's a better described as potential failure plane. But anyway, if you say it's failure plane, it's fine. Okay, but a more correct terminology is called potential failure plane. So if we have a major principal stress acting in a vertical direction and minor principal effective stress acting in the horizontal direction, we have soil element in the middle. So the potential failure plane will develop in an inclined direction inside, making an angle psi. Okay, later we will define this angle. Okay, but what is going on is actually is the we mobilize the maximum normal stress developed perpendicular to the potential failure plane. This is the normal stress. Okay, and then also the maximum shear stress sorry, it's tau maximum. This I'm running out of space. The shear stress develop across this potential failure plane. Okay, so it's this pair of normal potential normal stress and shear stress this pair maximum develop a lot. This is perpendicular to the potential failure plane. This is parallel to the potential failure plane. And it's this pair of normal stress and shear stress develop across the potential failure plane. Okay, normal stress perpendicular to it, shear stress travel along parallel. Normal stress perpendicular to the potential failure plane, shear stress travel along the failure plane, and if it is large enough, it causing the soil to fail, to slip, overcome the frictional resistance between the soil particle and slide failure. Okay, so it's this pair of normal stress and shear stress develop at the along the potential failure plane dictate will the soil fail or not, if it's safe or not safe. Okay, so let us go back. So 150 years ago, Professor Moore think that, when he developed the Moore circle for steel, for solid material, he think that. But then he realized for soil particle, it's more difficult. Okay, it's not solid. There's no bonding. So later, Professor Moore come along, and then they join together and develop this Moore Coulomb failure criteria, saying that, okay, if we plot it in a y-axis, okay, is the shear stress. Tau, that means the shear stress potentially develop across this potential failure plane. Potential failure plane is here. Okay, the shear stress that they potentially develop along this potential failure plane. So this is the shear stress. The y-axis is the shear stress, and x-axis is the normal stress. That means that the normal stress that potentially develop perpendicular to the potential failure plane, perpendicular to the potential failure. Normal, okay, this n is normal, so it's the normal stress, okay, to the potential failure plane. So what originally Professor Moore found out that by a series of experiments, I don't know how many days and nights of experiment, then we found out that the failure criteria, how soil fail between the shear stress and shear strain, it is a nonlinear line like that. Okay, but anyway, nonlinear line is sometimes difficult because to put in mathematical model because it's nonlinear, right? So we make the mathematical expression is very complicated. So Professor Moore come along. They all British guy. Okay, they are friend. Okay, in fact, Professor Moore is a student of Professor Coulomb. Okay, but after Professor Moore got his PhD, then he became a famous researcher, and then working with his PhD supervisor again, Professor Coulomb, and then try to see what is the best way to represent the failure of the soil. And then they found out that better simplify it, okay? And later they use a straight line instead of curve. This because the curvature is not very drastic. More or less, it could be represented by a straight line. Okay, so we find out that along this potential failure plane, the maximum shear stress developed along this failure plane. There's a almost linear relationship between the normal stress develop this normal stress, develop perpendicular to the failure plane. Okay, so it's this shear, the shear stress develop parallel to the potential failure plane, together with the normal stress develop perpendicular to the failure plane, will have a relationship. And this relationship is represented roughly by this straight line. Okay, so the soil, when a soil, say I have a soil, if my combination of the normal stress and shear stress is in here, okay, I have so much normal stress applied across the potential slip plane and so much shear stress applied across parallel to the potential slip plane. As long as the stress combination is below this red line, this failure criteria, this Moore Coulomb failure criteria, then the soil is stable, no problem. Okay, the foundation is stable, the slope is stable, the block of the soil is stable, there's no slip, no movement, no failure, because the internal friction, the granular friction of the soil particle is able to withstand this shear. Okay, everything is stable, no problem. Okay. Now they found that if we have a pair of normal stress and shear stress, just make the soil particle stay on the failure criteria, the red color there. Okay, we have a shear at that moment, just a failure. The normal stress and here, just a failure. Then, and sitting right at this straight line, the Moore Coulomb failure criteria, saying that the soil is just touching the, just fail. Okay, if the force is a little bit smaller, then it's stable. A little bit larger, then it fails. Right at that line is at the point of failure. Okay, that's the limit. How much combination of normal stress and shear stress that soil particle can support across this potential slip plane. If the shear stress is a little bit larger than the soil along that potential failure plane, which fail. Okay, so it's the criteria just saying that at that point, failure would develop. Okay, it's developing. Okay, if the shear stress is a little tiny little larger, then the soil mass would slide down. The soil will fail. Okay, now if we have a pair of the normal stress here and shear stress, it come to here. Okay, if we have calculated, okay, along a potential failure plane, the normal stress is this value, and then the shear stress is this value, then no, is above the Moore Coulomb failure criteria, then no doubt the soil mass would fail. Okay, so the soil will definitely fail. This block of the soil will slide down compared to the lower block. So the whole chunk of the soil will fail. Okay, so because of that, we define. Okay, let us recap again. Okay, this is the Moore Coulomb failure criteria represented by a straight line. Okay, it's across the space of it is the y-axis is the shear stress, the x-axis is the normal stress. Okay, now if we have soil with normal stress and shear stress causing it in here, normal stress is here, shear stress is here, the resulting combination of normal stress and shear stress here is still below this more Coulomb failure criteria. This this strict line, more Coulomb failure criteria, is still below it. Then the soil is safe, stable. The soil mass is stable, safe, no problem. Okay. Now, if we have a combination of the normal stress and shear stress, making the soil particle at B, this location, was sitting right at the boundary of the more Coulomb failure criteria with this normal stress and this shear stress. Okay, that means that the soil is just about to fail. Okay, it's right at the verge of failure， 即係開始破壞啦，開始冧啦。Okay, right at that point of failure. Okay, so it's triggering the failure mechanism， 即係開啟咗佢個泥土破壞啦，可能山泥傾瀉會發生啦，可能嗰個地基會冧啦。OK， 就啱啱開始破壞嗰啲。OK。Now, if we have a combination of stress, a normal stress is all here, it's the same magnitude, but then the shear stress is larger. Okay, the normal stress is here, but then the shear stress is larger, come to a point above the more Coulomb failure criteria, above this strict line, resulting in a shear stress in here, then definitely with a combination of normal stress and shear stress like that, the soil will definitely fail. 即係當我哋有個 stress condition， 個 normal stress 係咁樣，但係個 shear stress 就已經大過個 more Coulomb failure criteria， 即係多過呢度咧，過咗呢條線以上咧，喺呢一度咧，咁換句説話講，呢個泥土就冇可能冧，一定係冧咗噶啦。OK， 一定有 failure 發生嘅。OK， 所以咧就係呢條 more Coulomb failure criteria 咧就講俾我聽，我哋 combination of normal stress 同埋 shear stress 喺我哋嗰個 potential slip plane 裏邊，如果查下先 ，OK， 如果我哋係低過呢條 more Coulomb failure criteria 咧。如果我哋所有 stress stage 個 combination of normal stress 同 shear stress 令到佢嘅 combination 係喺呢條線，呢條線我哋叫 more Coulomb failure criteria， 喺下低嘅可能喺呢度，可能喺呢度，可能喺呢度，可能喺呢度，喺邊度得？咁換句説話嚟講，你嘅 soil mass 都係安全嘅 ，safe 嘅。OK， 如果你 combination 你嘅 normal stress 同埋 shear stress 令到佢啱啱起正呢條線咧，即係講俾你聽佢係 limit 啦，即係就嚟冧啦，最冧噶啦開始 ，OK， 起正呢個 more Coulomb failure criteria 就開始冧，即係 fatality 啱係1嘅啦。如果 shear stress 多少少，仲一聲就冧落嚟啦。OK， 咁即係冧緊嘅啦，你見到泥開始喐啦 ，OK， 個山泥傾瀉開始發生啦，快走啦！幾分鐘後嗰個山泥就冧落嚟啦，咁啱嗰個就嚟冧緊嗰個階段 ，OK。如果你計出嚟嘅 normal stress 同 shear stress 係 fall into 呢個 range 咧，咁死緊啦！即係換句説話，你設計嗰個 soil mass 嗰個 earth structure 就一定冧噶啦。即係如果你去到一個咁嘅 stress state 咧，唔穩定噶啦。OK， 我哋唔可以俾佢發生。如果因為個 stress state 去到嗰度咧，你個 earth structure 咧，無論你個係斜坡又好，你個 foundation 又好，呢條路又好，你嘅地基又好，一定冧噶啦。咁即係大鑊啦。OK， 所以咧呢個 more Coulomb failure criteria 好重要嘅。就講俾我哋聽，我哋設計出嚟嘅嘢，個 normal stress 同埋個 shear stress develop 喺個 potential slip plane 嗰陣時咧，究竟有幾大 係安全啦，定係危險啦，定係冧？OK，咁所以我哋一定要知，咁去 dictate 呢個安全同埋唔安全咧，就係我哋嗰個 more prone failure criteria 啦。OK， 呢條直線啦。OK， 好啦，咁我哋下一頁去講下啦。究竟呢條直線就係咩咧？嗱 ，before that we saying that okay, this more prone failure criteria is a boundary. Okay, between a safe and unsafe zone. Okay, right at this boundary, it's just talking about the soil is at the verge of failure. If your combination of normal stress and shear stress above this boundary, then soil mass would be fail. Okay, it's a failure line. It definitely fail. If the combination of the normal stress and shear stress is below this line, this criteria, then your structure is safe. Okay, so basically that is an important thing we are talking about. Okay, so now, as I mentioned before, the failure of the soil is developed across this potential slip plane. Okay. Okay. This, if you remember your soil mechanics of material, okay. If we plot the stress element, okay, we assume the major principal stress is in vertical direction. Now, since it's soil mechanics, we have to work with effective stress, not total stress. Okay. So major principal effective stress major principal effective stress, see the dash in here, acting on vertical direction. Okay. And minor principal effective stress is acting on the horizontal direction. Then in this case, your potential slip plane will develop inclination with angle theta from the major principal stress plane. This is major principal stress. This is major principal stress plane. Major principal stress plane, MPP. That means the plane where the major principal stress applied. Okay. In between them, it make an angle theta. This angle theta. Okay. While theta, actually later we can prove that. Later we will discuss the proof. Okay, is equal to 45 degrees plus the angle of friction divided by 2. Remember that. Okay. This angle inclination theta have a relationship with angle of friction theta of the soil. It will be always making at 45 degrees plus angle of friction divided by 2. Later you will find out why. But actually that is how it develops the maximum potential slip plane. Okay, so at this inclination is your potential slip plane at where the maximum normal stress will apply perpendicular to this potential slip plane, and then the maximum shear stress would develop across the potential failure plane. Okay, that's at that moment the normal stress and the shear stress is maximum across this potential failure plane. Okay, of course, the sigma 1, sigma 3, and normal stress and shear stress, they all have relationship. Okay, basically, by the technique that you learn in your mechanics of material, by this stress reorientation, stress rotation technique. Okay, later we will discuss. But anyway, remember that. Okay. Now, Mott Coulomb failure criteria saying that, okay, if at that point of failure we plot the normal stress, effective normal stress, with the maximum shear stress developed across the potential failure plane, then we will find out that all soil, the soil we are talking about, the soil mass we're talking about, that will be governed by this straight line. This straight line is the so-called Mott Coulomb failure criteria. Okay, it's a straight line. Plotting across the space on the y-axis. This is the y-axis. It's the shear stress across along the potential slip plane. This is the effective normal stress perpendicular to the potential slip plane. Okay. And as I mentioned before, below this potential Mott Coulomb failure criteria, everywhere in here, if your normal stress and shear stress fall below it, then your soil would be stable, would be safe. Okay. If your combination of normal stress and shear stress lie above this Mott Coulomb failure criteria line, then it's unsafe. Basically, you have failure. Your soil will collapse. Your soil structure, your soil mass will collapse. Okay. The criteria dictating is safe and unsafe is this straight line. Okay. And if relating the normal stress, effective normal stress, and then the maximum shear stress develop along the potential slip plane. Okay. The equation of this straight line, let me clean out this thing. The equation of this straight line to this straight line to define these two zones is the famous Mott Coulomb failure criteria. It says that this is the maximum shear strength that develop in the soil across the potential slip plane. Okay. Here is the cohesion, soil cohesion, or cohesion, soil cohesion intercept. It's basically here is the shear stress. Here is the shear stress versus normal stress. Now zero is here, origin is in here. Okay. So here we just join extending to the negative side. Here is a positive normal stress. Here is the negative normal stress. Tension, that's mean here is tension. Here is compression. Remember, for soil mechanics, compaction positive. So we have compassive force. Okay. So the Morgan criteria actually, if you just look at the positive normal stress, will be here, from here to there. This is the cohesion intercept. That means that when the normal stress is 0, the cohesive strength, okay, this is C dash, cohesive intercept. For granular soil, C dash is 0 for granular soil. That means for sandy soil, okay, because sandy soil is granular soil, the most important constituent is sand particles. So when we talk about granular soil, basically it's sandy in nature. There's no cohesion, not like clay. It's cohesive， 即係唔係好似 clay 即係黏土咁咧。咁我哋中文 clay 就叫黏土啊。點解叫黏土咧？因為佢有個黏性會黐手嘅。OK， 咁咧呢啲黏性喺邊度嚟咧？就係呢個 cohesion intercept 啦。OK， 呢個 cohesion intercept 咧就大過0嘅，唔係0嘅嚇，係正數嚟嘅 positive 嘅。呢個咧就係 cohesive soil。因為黏土咧，大部分嘅黏性咧就由 clay mineral 所做出嚟嘅。而 clay mineral 咧，佢有 fictional 啊，但係咧佢 clay 同 clay 之間咧就仲有呢啲 electrolytic bonding 嘅。咁咧我哋摸落去咧就好似黏手啊，即係嗰啲 clay 土好黏性，嗰個黏性咧就變成呢個 cohesion 啦。OK， 所以咧喺嗰個 fine grain soil， 即係個 clayy soil 或者 cohesive soil 咧，咁咧佢除咗有個 angle friction 之外咧，佢仲有個 cohesion intercept 嘅，即係講俾你聽，就算佢係冇 normal stress 之下，佢本身都有少少 cohesive bonding 嘅，少少 ，OK， 所以咧 for cohesive soil 咧。咁我哋再拆翻去。咁咧，我哋個 failure criteria ，shear stress failure 等於 cohesion intercept plus the normal stress, effective normal stress times the tangent of angle friction. OK。咁 for granular soil 即係 sand 啦、gravel 啊嗰類啦。咁咧個 cohesion intercept 咧就係0嘅 ，OK。因為咧 granular soil 咧係冇 cohesion 嘅，冚唪唥咧100%咧都係靠 frictional resistance generate 出嚟嘅啫。所以咧 for granular soil 咧個 failure criteria 咧就會 simplify 成咁樣啦。個 C 係0啦，呢度冇錯啦，呢度0啦。咁即係 normal stress effective normal stress 乘以 tangent angle of friction。OK， 呢個 granular soil， 因為 cohesion intercept 佢冇 cohesion 嘅 granular soil， 即係 sandy soil 啊、gravelly soil 啊、silty sand 啊咁，因為佢個 cohesion 係好少嘅。cohesion 係 clay 個產生嘅 ，clayy soil 產生嘅，所以 sandy soil 咧 ，granular soil 咧就冇 cohesion， 呢 cohesion 就等於0。咁呢條 equation 咧，呢條0咧就簡化成咁樣。OK， 咁嗰個 relationship between shear stress and failure 就等於個 effective normal stress 乘以 tangent of angle friction， 呢個就係 granular soil。OK。咁 for cohesive soil 咧，即係 clayy soil 嗰啲啦，即係有黏土啦，燒啲 clay 啲燒啊 ，sand 啲 clay 啊嗰啲咁咧，即係有黏土好大部分嘅黏土裏邊，佢天然咧就有 cohesion 噶啦。 OK， 咁佢嘅 shear string failure 咧就等於 C dash 即係呢個 cohesion intercept， 因為佢本身就算係冇 normal force 都好，都係有少少 cohesion， 因為呢啲 cohesion 咧就由 clay 嘅 mineral 嘅 electromechanical effect 所產生嘅，所以咧佢點都會有少少 cohesion， 就係我哋黏土點解黏手嗰種黏性就係呢個 cohesion intercept 啦，再加上 normal effective stress 乘以 tangent angle of friction。OK， 所以佢嘅 string 咧一就 come from cohesion 啦，有少少呢個 value 唔會好大，可能幾個 kPa， 可能10個 kPa， 唔會好大啊，即係點都細過20個 kPa 嘅，通常幾個 kPa 至到20個 kPa 之間，但大部分嚟講咧都係呢個 friction 嘅 ，OK， 呢個 frictional resistance。OK， 所以咧 cohesion soil 咧 cohesive soil 咧，佢嗰個 shear string mobilize 咧就兩 part， 一就係 cohesion 嘅 cohesion intercept 就呢度，第二就係嗰個 friction 啦，咁啊 friction 咁啊梗係要睇我哋嗰個嗱呢條 line 呢個就 Morgenfeld criteria， 咁我哋 measure 呢一個 slope 咧，呢個 angle 咧就係我哋嘅 cohesion 即係 angle of friction 啦。OK， 佢係呢條線係直線嚟嘅，所以個 slope 係邊度 measure 都一樣嘅啫。咁呢個 slope 咧就係 cohesion intercept。嗱，不過好多同學 plot 呢個圖嗰陣時咧都唔小心嘅，我考試都唔知扣過幾多分㗎啦。就係呢個 shear stress 同埋呢個 normal stress 係 same scale 嘅。唔該你哋記住啦，真係我無數次嘅錯誤咧，就係啲同學就咁 plot 出嚟，但係佢個 x scale 咧，即係嗰個 normal stress 咧就有個 scale，y 咧求其又攞咗另外個 scale， 另外攞另外個 scale 係唔啱嘅，唔啱。OK，x 同埋 y 係一定要 same scale， 即係要個 square 格仔紙嗰度 plot 出嚟嘅。嗱，好多同學咧就求其揾 Excel plot 出嚟，但係又冇睇佢個 scale。嗱，你 Excel 就咁 plot 出嚟咧，如果你唔 instruct 佢個 x scale 同 y scale 係用 same scale 咧，咁個 Excel 咧就可能 x 又抄嗰個 scale，y 又另外一個 scale， 咁就有 plot 出嚟。咁同學就喺嗰度 measure 個 angle 咧，咁就肯定錯到飛起啦。OK， 好多每年咧都有一半咧嘅同學，我哋叫你你 plot 個即係當你哋做完嗰個direct shear test 或者 triaxial test 啦，你 plot 個 normal stress versus shear stress 出嚟啦，然後 measure 個 cohesion intercept 同埋 angle of friction 啦，咁有半班咧都係 plot 錯，plot 啱嗰啲咧通常用手 plot 喺格仔紙個 plot。咁格仔紙 x scale 就同 y scale 一樣啦，咁啊冇錯啦 ，measure 嘅 angle 就 correct 啦。咁另外嗰半班就冷啦，就係打落去 Excel 嗰度。但係咧Excel 都可以做嘅，但係你一定要講到明嘅，聽個 x scale 係等於個 y scale 咁。但係佢係冇做呢個 step， 就咁打啲數值 x 嘅 value 係乜 ，y value 係乜，咁就 plot 咗出嚟，又冇去拉嗰個 scale，make sure x 同埋 y 係同一個 scale， 係 square 嘅嚇。咁啊就走就咁 plot 出嚟，咁就喺度度個 angle， 咁啊錯啦。所以有一半班咧嗰條咧都錯晒。OK， 半班啱，半班錯，即係大樣啦。因為咧一半咧就冇去理個 scale， 咁啊求其啊 plot 出嚟，咁啊喺度交咗就算。呢啲係真係錯。求其啦，唔得㗎！我再講一次，我哋 plot 嗰陣時 ，OK，shear stress 呢個 scale， y scale 係一定要等於 x scale。OK， 一定要。咁你喺呢度 measure 呢個 angle 就係 angle of friction 就啱。measure 呢一個 value 當normal stress 係0，啱啱喺 origin 嗰個對象，呢個就係 cohesion intercept， 咁就啱。OK， 好多時同學係咁以就撲落去 Excel， 冇 reinforce 到 x 同埋 y scale， 咁冇咧個電腦就好蠢嘅啦，全世界最蠢嘅就嘢係咩咧？就係個電腦啦，梗係蠢過你阿媽嘅真係。咁咧佢就唔理噶啦，就咁啊，總之撲出嚟算嘅，就翻佢圖形咁啊。所以咧就大部分嘅 x scale 唔等於 y scale 嘅。咁所出嚟咧，佢話嗰個 angle of friction 咧，就如果你就咁度出嚟咧，就一定錯到飛起嘅，錯到你阿媽都唔認得噶啦。OK， 咁啊 cohesion intercept 就係睇 value 嘅，咁就唔會錯，係個 angle of friction 就錯。所以咧再講清楚啦，你哋一係就喺格仔紙自己用手 plot， 如果唔係用 Excel plot 咧，就 make sure 個 x scale 係等於 y scale，plot 出嚟咧係 square 嘅。每一張紙喺呢度係 square 嘅 ，OK？X 係等於 Y 嘅，然後喺嗰度先至拉嗰條線，呢個然後呢個 angle 就 angle of friction 啦，咁先啱嘅。一定要呢 normal scale 個 x scale 同埋 shear stress 個 scale y scale 係一樣嘅。OK， 一樣嘅嗱，好多同學都 miss 㗎啦。我依家又係咁講啊，我唔知有幾多，即係始終係 internet 啦，我哋唔知你哋幾多人真係認真咁聽啦。真係有啲人喺度瞓覺，有啲人喺度打機，有啲人喺度睇緊電視啊，唔知道你做咩啊。但係即係嗱，再講一次 ，x scale 一定要等於 y scale 先至 pop 出嚟，然後度個 angle internal friction 先至啱㗎。因為真係年都係咁講，年都同學都係咁錯嘅 ，OK 就係咁以揾個 Excel 就 plot 出嚟，咁個 x scale 又唔等於 y scale。如果 Excel 係可以 plot， 但係你一定要講俾佢聽 x scale 等於 y scale。如果唔係佢係咁以 plot 落張圖 x scale 唔等於 y scale， 咁你咧個 angle of friction 咧就錯㗎啦 ，OK？ 所以記住啦，咁 angle of friction 咧就喺呢度度出嚟。個 cohesion intercept 咧就喺呢度度出嚟，即係再講多一次，唔好嫌我煩。cohesion intercept 呢個位 ，OK， 當 normal stress 係0嗰時，喺 origin 度上去呢個就 cohesion intercept。咁當 x 同 y scale 一樣，咁喺呢個 small Coulomb-Farrell criteria， 咁呢個 angle 咧就係 angle of friction 啦。或者叫 internal angle of friction，OK？ 咁就完成咗我哋呢一個 equation more Coulomb-Farrell criteria shear stress failure 就等於 cohesion intercept 加以 normal stress effective normal stress 乘以 tangent of angle of friction 或者 internal angle of friction，OK？ 咁呢個就係我哋個 more Coulomb-Farrell criteria 講俾我聽，如果個 shear stress 係 below 呢個 value 咧，咁我哋個 soil mass 就 safe 啦，我 soil structure 就 safe 啦。如果佢等於 shear strength 係等於呢個，咁就啱起正呢個 more Coulomb-Farrell criteria 就啱開始冧啦。如果呢個 shear stress failure 係大過呢一抽嘢咧，就換句上嚟講，佢就喺呢度上邊啦。OK， 咁即係換句上嚟講，你個 soil structure 咧肯定就冧噶啦，一定 fail 噶啦。OK， 咁你要重新再設計過啦，因為喺呢個 moment 係 unstable 嘅。OK， 咁所以呢個係重要嘅。OK。我仲有一個講 ，OK。Another thing in here is the From the major principle, if you remember how to manipulate those small circle, from the major principle plane, from the major principle stress plane, you measure to here. This right here is the failure point. That means that at this right at the point of failure, that is the normal stress at failure. This is the shear stress at failure. So you only wow. So solve element 呢？呢個 major principal stress. This is major principal stress. This is minor principal stress. This is the potential slip plane. Okay. This angle is theta. Okay. It's related. This theta is related to this 2 theta. Okay. Here, this angle is 2 times the value of if we plot it in here in the saw element, this theta. They are related. Okay. In Mohr circle, it's 2 theta. In the actual saw element, is theta. Okay. Now, this is the potential failure plane. Okay. And then the normal stress at failure, the effective normal stress at failure is here. The shear stress at failure is here. Okay. The shear stress at failure is always parallel to the potential failure plane. This one. Okay. While the normal stress at failure, the name normal, that means they are normal to failure plane. That means 90 degree. Normal 即係90度咁嘅意思啦。OK， 英文我話 normal stress 就即係嗰個 stress 同個 failure plane 成90度 perpendicular 嗰個 stress 就叫 normal stress。OK， 咁normal stress 即係90度成個 failure plane 喺呢度，個 normal stress 就係90度，90度。OK， 咁壓落嚟同個 failure plane 90度呢度。OK， 咁情形之下咧，呢個 Mohr Coulomb failure criteria 就話啦 ，shear stress at failure, right at the point of failure, the relationship between shear stress and the normal stress is like that. Shear stress at the failure plane at the verge of failure is equal to cohesion intercept of the soil plus the effective normal stress developed perpendicular to the potential failure plane times the tangent of angle of friction. Okay, so this is what we mean by this equation. Okay, so this is Mohr Coulomb failure criteria saying that if we want to tell under what shear stress your soil will fail, under what shear stress your soil is safe, the relationship can be simplified by this equation, this linear equation. We have 2 soil parameters that we need to take attention. One is cohesion intercept, and one is the angle of friction. Okay, so cohesion intercept is here, angle of friction is this angle. Okay, but make sure when you measure this angle, you have to plot in shear stress in the y-axis, normal stress in the x-axis, but they have to be in the same scale. Okay, not different scale. If it's different scale, then you measure the angle. Obviously, it's not the true angle. Have to be same scale. Okay, square paper. Okay, even though you use an Excel to plot it out, make sure you add the function saying that the x scale is equal to y scale. Okay, or when you pick the scale, you pick Y scale same as X scale. Okay. Now, to further complicate you, okay, actually, remember, we're saying that, oh, this is the salt element, okay, this is the potential failure plane, okay, this is the normal stress, effective normal stress perpendicular to the failure plane. This is the shear stress developed along the failure plane, okay, but they can relate it to our normal stress, major principal stress, and minor principal stress. Okay, if you remember, okay, in Morse circle, the stress reorientation you learn in your mechanics of material. Okay, any stress in any given direction can be related to any pair of the stress in any other direction. Okay, so it just happened to be, okay, if we find out the potential failure plane is here, making an angle theta with the major principal stress, okay, that's a relationship between the normal stress at failure and shear stress at failure with the major principal stress and horizontal principal stress. Okay, the relationship is here. Okay, now make sure you remember that, because in the exam we always ask you, okay, you calculate the normal stress at failure, you calculate the shear stress at failure, but we just ask you then, what is the major principal stress at that point of failure? What is the minor principal stress at that point of failure? To relate the major and minor principal stress at the point of failure with the normal stress and shear stress at the point of failure is these two equations. Okay? Normal stress at failure is equal to the major principal stress plus the minor principal stress divided by 2. If you plot the Morse circle, actually it's like that. Here to the center of the Morse circle. Minus this little guy. Minus here is that. Minus major principal stress minus minor principal stress divided by 2. So it's the radius of the Morse circle times sine of the angle of friction. Okay, so this equation relating the normal stress at failure with the major principal stress sigma 1 and minor principal stress sigma 3 with the angle of friction, fine. Okay, while the shear stress at failure can be related, just this value here, okay, can be related to the radius, that's mean major principal stress minus minor principal stress divided by 2 times cosine angle of friction. That means we just doing this, decomposing it in here. So you have to, from here to here, subtract here, then you get the normal stress. Now here is your log. If I put here is the normal stress at failure and shear stress at failure. This point, the failure point. Okay, the normal stress at failure, the shear stress at failure. Okay, so at that point is the soil with the combination of major principal stress 1, minor principal stress 3, then the soil element fail along this potential failure plane with that pair of normal stress and shear stress. the value, the relationship. That okay. So that's mean that we can give you the major principal stress and minor principal stress and the angle of friction to ask you what is the normal stress at failure and the shear stress of failure. That's one way to ask. Or we give you a problem, then you figure out the at the point of failure, the failure condition, what is the normal stress at failure, shear stress at failure. From that, we figure out the angle of friction. From that, we use these two set of equation, find out what is the major principal stress and minor principal stress. Okay, so there's that many different ways to ask you. So in the tutorial, we definitely will produce an example. So you have to know how to transfer the stress from the normal stress at the failure plane, shear stress at the failure plane, and relate back to the major principal stress and minor principal stress at failure. Okay? Now make sure those definition, the meaning of this, if you don't understand, you better read this slide very, very carefully, okay? Because the entire section of shear string require you to understand this Mohr circle thing, okay? And the Mohr circle thing, I am sure you already learned it in your mechanics of materials, in your first 2 years of your high diploma program, okay? So there's no excusing, oh, I don't know what you're talking about, because every higher diploma student graduate from civil engineering must understand that. Otherwise, you should not graduate, okay? So by the time you take the degree, you should understand this concept, okay? So maximum shear stress and maximum normal stress develop along the failure plane can be related to the major principal stress and effective principal stress by these two equations. Remember that, okay? Now, and to further elaborate, you with in here we since we are doing just undergraduate, so we assume the soil we have the same pit state and the critical state. Okay, we are not learning critical state soil mechanics. So in this case, we assume a critical state condition of the soil is same have the also is the pit state that limit. We just learn limit state. What you are learning in limit state soil mechanics. So limit state soil mechanics to assume the soil at the pit state is equal to the soil at critical state. So the relationship that I show you apply for both critical state and pit state. Okay, so basically that is the we're learning limit state soil mechanics. Okay, so we don't make the distinction between them. But of course, if you go along, if you go to postgraduate study or using the more advanced soil mechanics theory, then we know that critical state is not equal to pit state. Critical state is closer to the residual state of the soil, while pit state is pit state. Okay, so but anyway, at here this point, just assume they're the same. Okay. Okay, so we summarize what we learned in the Mohr-Coulomb-Farrell criteria. Okay, we are coupling the Mohr circle with the Coulomb-Farrell frictional law. Okay, to develop this Mohr-Coulomb-Farrell criteria, and so that's what we use. Okay, and then from the Mohr-Coulomb-Farrell criteria, we can find out what is the maximum shear stress developed at the failure plane, and then the maximum normal stress developed at the failure plane. Okay, and this stress can be related to the major principal stress and minor principal stress by the two equations I show you. In the Mock-Coulomb failure criteria, the equation is the shear stress at failure is equal to cohesion intercept plus the normal stress at failure times the tangent of the angle of friction. Okay. So Mock-Coulomb failure criteria is a straight line which composed of two soil parameters. One is the cohesion intercept. For granular soil, cohesion intercept is equal to 0. For cohesive soil, fine-grained soil, the clayey soil, cohesion intercept is larger than 0. Okay? And another soil parameter is angle of friction. Now, just to talk a little bit more, okay? For granular soil, the same graph that came. Angle of friction typically between 30 degrees to maximum maybe 40 degrees. Okay? While cohesion intercept is equal to 0. Okay? For cohesion intercept, cohesive soil, fine-grained soil, cohesion intercept small, maybe somewhere from 5 to 20 kPa. Angle of friction around 20 to 25 degrees. Okay? Typically. Not always, but from my experience, okay, soil we find in Hong Kong, basically that is the case. Okay? Granular soil cohesion intercept yield 0, angle friction somewhere between 30 to 40 degrees. For cohesive soil, fine-grained soil, clayey soil, cohesion intercept is not 0, a small value, somewhere from few kPa to maybe around 20 kPa maximum. Okay, around 5 to 20, around. Okay, angle of friction is smaller, usually around 20 to 20, 25, maybe 26, 27. I still see it. For some over-consolidated clay, the angle of friction may be higher. Okay, closer to 30. But for soft clay, then it generally is low. It's around 20. Okay, put it down, drop it down, because that I don't think it's discussed in these notes, but if you're doing your practice in geotechnical engineering, there's some number you should know. Okay, otherwise your supervisor saying that which university you come from, such a typical value you don't even know. 又俾人笑啦！你出去啱啱做嘢嗰陣時咧，頭嗰幾年咧就俾嗰啲大佬咧嚟當你嘅科咁樣踢，咁啊，然後跟住咧就話乜都唔識嘅，冇用嘅你哋出嚟，咁啊喺你背後啊講你一大扎你壞話。我哋學嗰陣時呢啲冚唪唥學過晒啦，搞錯你哋而家出嚟乜都唔識，即係實會咁講，樣樣都要問我。OK， 咁你又所以咪做人爭氣啲咯，學多少少咯嚇。因為你 RMIT 嘅課程咧，真係比港大同埋科大係簡單好多。咁所以佢哋有睇你哋實串你哋嘅啲大佬，咁你大佬多數得呢幾間 U 嘅啦，做到大佬嘅多數都唔係香港 U 就科大嘅啦，或者最多City 同 Poly 就嗰啲人做多幾年都會做大佬嘅，咁但係搞錯啊！我喺 Poly 嗰時都學過啦，你哋未學，咁實會喺背後話你哋，咁啊唔好衰俾人睇啦 ，OK？ 咁呢啲咧佢哋都要學噶啦，咁你記住啦 ，OK？ 雖然呢個錄視冇 ，OK？ Okay, we go to the next chapter that continues to discuss our shear strength of the soil. Let me drink something. Just getting at the thirsty. And we still have almost 4 o'clock. We'll have another hour or so. Okay, let's continue to discuss the shear strength of the soil. The interpolated shear strength of the soil for this. I think this is a further with your example. Okay, I think this is just an example. Okay, understanding the soil parameter where you can extract from test data. Okay, for completion of the Moore Coulomb failure criteria, the soil parameter, the cohesion intercept, and then the internal angle friction. Okay, usually we will find for the Moore Coulomb failure criteria. Okay, so this two soil parameters we need. These two soil parameter we will determine from laboratory test. Either use direct shear test or triaxial test. I understand that we will have a lab. I think will be on October 15, something like that. Let me check. I forgot. I think I saw an email. It's on Thursday evening, something like from. Not totally sure. Is it from 7 to 9 or 6 to 9? I forgot. Okay, but in the geotechnical lab, the lab just across from the concrete lab. Okay, so we will learn the direct shear test. Oh no! You will do a consolidation test and direct shear test, and wait until you go to next year. You learn geotechnical engineering 3, then you learn the triaxial test. I think it's like that. But anyway, direct shear test or triaxial test will help us to define the cohesion intercept and angle of friction of the soil. So to complete the Moore Coulomb failure criteria. Okay, so this two soil model. Okay. So in here we simply just go through example, saying that usually in triaxial test we prepare a soil cylinder, soil, and then put in the triaxial apparatus. Okay, then we will apply a major principal stress in the vertical direction. Okay, in this example, major principal stress is equal to 300 kPa. Okay, like assuming like we haven't talked about the principal or triaxial test. Next section we will talk about it. But assuming okay, this is a soil sample. Okay, it's in cylindrical. We usually trim it in a cylindrical shape, and then mount it in a triaxial mold, and then apply a major principal stress in the vertical direction, which is 300 kPa, and minor principal stress along the radial direction of your soil cylinder. Usually apply full water. It's a water pressure. We got confining stress. This is major one of the maiden hole. And minor principal stress 3 is 100 kPa. Okay, minor principal stress is 100 kPa. So in this example, we have a soil specimen, cylindrical in shape, put in a triaxial cell. Okay, from that we apply a confining pressure of sigma 3. Confining pressure. Actually, it's equal to sigma 3. Okay, we put in a sample in a triaxial cell, and then all around it apply with water pressure. This water pressure, we call it confining pressure. We confine the soil with water. We put water, we pressurize it. Okay, in this example, the confining pressure is 100 kPa. So 100 kPa, that means 1 atmospheric pressure. Okay, but compared to our normal atmospheric pressure, we are under now 100 kPa. We add another 100 kPa full water onto the soil sample. But on top, okay, on the vertical direction, we apply. Now, originally it have the water pressure. Water pressure is hydrostatic everywhere, right? Horizontal, vertical. So when we apply the hydrostatic pressure of 100 kPa, then we already in the vertical direction at 100 kPa. But on top of it, we add another 200 kPa. So making the major principal stress, the major principal vertical stress, that's mean 100 plus 200 is equal to 300 kPa altogether of vertical effective stress applied on the soil. Okay? So we say that at that moment, the soil start to fail. Okay? It just fail at that moment. Okay? With vertical effective stress, sigma 1 of 300 kPa, confining stress, sigma 3 of 100 kPa. And the soil just at that point start to fail. Okay? We ask you to determine the friction angle, okay, and cohesion intercept, if any, okay, and then the failure plane. Where is this failure plane? What is the normal stress at the failure plane? Maximum normal stress at the failure plane, and then the shear stress, maximum shear stress along the potential failure plane. This is the potential failure plane. Oh, okay. This is a major principal stress plane. Major principal stress applying this direction, making inclination fine. What's this angle? Okay. So actually, we discussed that. You saw the equation. We just make use of it to do the calculation. Okay. Okay. This is what we discussed. This is a major principal stress, sigma 1. It's 300 kPa. Minor principal stress applied to here, 100 kPa. Then at that point, failure plane start to develop. Okay. First of all, we want to ask you the angle of friction. Okay. Even though it asks critical state, as I mentioned before, in here, critical state equal to pitch state. So it's the same. We just assume critical state is equal to pitch state. Okay, so no difference. Okay, so now if you remember, I show you this equation. Let me go back a few PowerPoint first. I show you this equation before. Here, this equation. Okay, this is the shear stress, maximum shear stress along the failure plane. Okay, and then it's the angle of friction. This is a major principal stress. This is a minor principal stress. Okay, yeah. This way, you can use this equation to calculate the angle of friction at critical state or the pitch state. And then once you find this angle, then you substitute in here. Then you can find the shear stress, maximum shear stress along the potential failure plane. Okay. And also this equation. And also, if you have the major principal stress and minor principal stress at the state of failure, you can also use this equation if you know if you find out the angle of internal angle of friction, you can relate the normal stress at failure and the shear stress at failure also using this equation. So you have this 1, 2, 3, 4. This 4 set of equation is important. Okay, so we make use of this equation to solve the question we just discussed. Go back to here. Our major principal stress at failure is 300 kPa. Our minor principal stress at failure is equal to 100 kPa. Okay. Now remember, I showed you this equation before, right? Just previous slide. But so first of all, we want to find out the angle of friction. Since in here we just requested they're the same, okay? Maximum internal angle of friction is equal to critical state angle of friction, because in undergraduate level we didn't differentiate the difference between the two. So just assume they're the same, okay? So the relationship between angle of friction and major principal stress is like that. Now we know sigma 1 is 300 kPa, sigma 3 is 100 kPa, so we substitute in here 300 minus 100 over 300 plus 100, and then take an arc10 outside. The angle of friction is equal to 30 degrees. Okay, and then second is we want to find out this angle. Okay? The angle inclination. That's mean this failure plane. What's this angle? As I mentioned before, this angle, this fine, I'm sorry, I'm using wrong. Fine. This angle inclination is always equal to 45 degrees plus angle of friction divided by 2. Okay, this equation we discussed before. So now we find out the angle of friction is 30 degrees. Just substitute inside 45 plus 30 over 2, 15. So this inclination angle, this inclination is 60 degrees. Okay, the failure plane. This is the failure plane. Making 60 degrees from horizontal. This horizontal is also called the pole, major principal stress plane. Okay, this one, major principal stress plane is 60 degrees by this equation. Okay. Now, furthermore, okay, we want to find out the normal stress at failure and then the shear stress at failure. That means that while at this failure plane, if we want to just extend it, we want to find out what is the normal stress at failure, what is the shear stress at failure. Okay. Now, again, and before that, we show you another equation relating normal stress, sigma 1, sigma 3, and angle of friction. I just showed you, okay, in the previous slide. We have sigma 1, we have sigma 1, sigma 3, and the angle of friction we just calculate from here, okay? So now we have everything. We substitute into this equation, find out the normal stress, which is 150 kPa. The normal stress at failure is 150 kPa. Okay, and then shear stress at failure. We have this equation we discussed before. We have normal stress major principal stress, minor principal stress, angle of friction. So major principal stress 300 minus minor principal stress 100 divided by 2 times cosine of the angle of friction, which is 30 degrees. So you punch in the calculator, find out shear stress at the point of failure is equal to 86.5 kPa. So that means along this potential failure plane, the normal stress at failure is 150 kPa. The shear stress at failure it is 86.5 kPa. Now, if I plot it didn't ask you to plot, but I just do it for you. Okay, if I plot this is the maximum shear stress. This is the maximum normal stress. Okay, so in here we don't know the cohesion intercept, but we know that the angle of friction is 30 degrees. So the Mach Coulomb failure criteria is here, and your normal stress at failure is 150 kPa. 150 kPa. Your shear stress at failure here is 86.6 okay, kPa. So right here. Okay. So this angle is 30 degrees. Okay. So basically, if you want to complete your Mohr circle, this is a Mohr circle. Okay. Major principal stress here, 1, 300 kPa. Minor principal stress here, 100 kPa. Center is 150 kPa. Okay, so this angle here is 60 degrees. Greater. Okay, if you want to completely plot out the Mohr circle, everything put it in a diagram, it will be like that. Okay, but in this question it didn't ask, but in your midterm or final exam, sometimes they ask you to plot it like that. Okay, since you have all the values, you can easily just plot it out. Okay, understand? Okay, so I just complete this example in here. Okay. Okay. I just completed, so there's no need to go through this question. Okay, so we just complete that example. Okay, there's more example in the tutorials. Okay, although I may not have enough time to go through the example today, but uh, I think I already sent you the questions and the answers. So over the holiday, I hope you can spend some time to look at it yourself, okay, and try to understand it. And then next week is a holiday. It's a Mid-Autumn Festival holiday, so there's no school. No, it's the 1st of October. Okay, I don't know how patriotic you are. Anyway, welcome for the Hong Kong people to go back to the communist China. So let's celebrate with damn COVID. Anyway, don't want to talk about politics. But anyway, we don't have class next week. But anyway, I will try to finish all the formal discussion of lecture and the tutorial question and answer already emailed to you, so you can take a look of yourself, okay, and then do a little bit of self-study. And then the week after that, I think we will go back to the face-to-face lecture. So I have to check which class lecture room. I think they sent the ship people, KM sir, or they sent us the location table, but I haven't checked. But anyway, that week we will start our face-to-face discussion. So I will go through a few more examples, select from your tutorial, okay? And then after that, we will talk about the next lecture, okay, on the Earth pressure coefficient. Okay, so today let us finish that. Okay, now we know the importance of the soil parameter. We discussed the Morse-Coulomb-Fourier criteria, the cohesion intercept, and the angle of friction. Okay, it's important because later, oh, the last section we learn, the last two sections we learn. One is on the slope stability, and another topic on the bearing capacity. Then we need to use those soil parameters, the cohesion intercept, and then the angle of friction. Okay, for the design. So you know those are the important soil parameter. In this chapter, we just talk about the concept, why is there. Okay, in here we will just talk about the lab and what kind of lab we can use to determine these two shear strength parameter. One is direct shear test, one is a triaxial test. Okay, but anyway, the best is for you. We will go through the direct shear test by the time that you have a much better understanding of how the test goes. Here, I just roughly go through some procedure. Okay, and then the major layout of the apparatus. But anyway, nothing better than an actual test. Then you will learn how to do it. Okay. So anyway, the main purpose of the lab test is determine and to extract the soil parameter. The soil parameter for the shear strength of the soil is cohesion intercept and the angle of friction. These two parameters can be determined either by direct shear test direct shear box. This one we will go over in the lab, I think in October sometime. Okay, I will be there. Okay. Another one is the triaxial test. If I remember correctly, triaxial test, you will learn it to do it in your geotechnical engineering 3, because it will take a little bit longer time for the setup of triaxial test. So we wait until you go to next year to do it. Okay. But anyway, the concept of direct shear test and then triaxial test is quite similar. Both of them is to help you to determine the Morse-Coulomb-Fourier criteria. In that will help us to determine the cohesion intercept and the angle of friction. Okay. Okay. So this is the two tests, but I think we will focus more on the direct shear test, okay, because that is the actual test you do later in October. Okay. Now here is the apparatus of the direct shear. This is direct shear box, and this is the testing apparatus. Now this testing apparatus is a computer control one, but the one you are learning when you're going to the lab is a manual one. Okay, so you have to do everything by hand. This one, you program everything on a computer, and then the computer will control the test, and then you just sit there, okay, drink your coffee, and then the computer will do everything for you. You don't have to take any data whatsoever. The computer will do it for you, and then you can ask the computer plot out all the results, calculate all the value, and print it out, and then you just put it in the report. That's all. Okay, but to make sure you learn, we will do the manual one. Okay, so every damn thing you have to do it by hand. Okay, and then all the value you have to. That teammate, a group of students have to take the data one by hand, and then plot it out Okay, so you learn it the hard way. Okay, okay. Basically, a direct shear box is like that. I don't know. I can enlarge this figure. Okay, just I enlarge it like that. Okay, this is this guy. So basically, we put the soil in this shear box. Okay, this is the soil inside, and then on top we apply a normal stress, and then we shear it with a shear stress until the soil fill along this PE, find the failure plate. Because basically, you see the shear box have this upper box and the lower box, so it will force the soil to fail in between the upper and lower box. The soil will definitely fail in here. Since we know the normal stress we apply, and then we measure the shear stress at the point of failure, then we know normal stress and shear stress, then we can figure the angle of friction. So as simple as that. Okay. So basically, let us go to the lab and detail arrangement we will discuss by then. Okay. Okay. And triaxial test. Now we don't have time to go through the triaxial test, but the idea in here is we have the soil specimen, cylindrical soil specimen, trained and mounted in the triaxial apparatus, and inside there's a cell. You see this plastic glass cell, and it's filled with water. First, water. Then water will be pressurized. Then the entire soil sample, when we pressurize the soil, okay, when we add water supply here, it will go in and pressurize an entire chamber. Okay, so all the soil specimen will subject to sigma 3 hydrostatic pressure. And then after that, you see this piston. Okay, this piston will apply the additional stress through this piston, okay, in a vertical direction until a failure. So your sigma 1 will be equal to your additional stress we add through the piston plus the original confining stress. Then we figure out the major principal stress. And inside we also have a pore pressure transducer. We can measure the pore water pressure. Since we know the pore water pressure, then we can figure out both drain the parameter and undrain the parameter. Okay, so in that way, then we can find out the soil under undrain tests fail under undrained condition, and the soil fail under drain condition. While the direct shear test, we cannot control water pressure. The difficulty of triaxial direct shear test is we cannot control water pressure. So basically, for direct shear test, we do it treat as drained test. So basically, we determine is the drain the parameter. C dash find dash drain the parameter. It's under drain the parameter, not undrained. It's drained. Because in direct shear test, we cannot control the pore water pressure. So usually we do it very fast, but allowing all the water pressure to dissipate, excess pore pressure dissipate. So we assume it's drain the test. Okay. While direct shear test, we can control the drainage path, drainage valve, so we can either do it as drain the test or undrain test. Okay, so we can find out the drain the parameter under drain the condition. Then we can find out the cohesion intercept under drain and angle of friction under drain condition. We can do it under undrained test. So we can control the drainage valve. We can close the drainage valve and simulate undrained test. That means no time, no chance for the pore pressure to dissipate. Pore pressure will lock into the soil element. So we will determine the undrained cohesion intercept. U in here stands for undrained, and also undrained angle of friction. U. So every time you see a U, subscript U in here, it stands for undrained test. So CU, find U. Talk about cohesion intercept under undrained condition, angle of friction under undrained condition, or fully drained test. Cohesion intercept under drained condition, so it's dash. You see a dash in there. Angle of friction under drained condition, you see a dash in here. Okay, so triaxial test can do both drained test and undrained test. Find out the drained C dash, find dash, or undrained CU, find U. Okay, CU is undrained cohesion intercept, find U is undrained angle of friction. Okay, so that's the advantage of triaxial test. But I think triaxial test you will do it, you will learn it next year how to do it. Okay, it's more complicated the setup. Okay, this October we will only do the triaxial test. Now, since a triaxial test could be quite complicated, okay, because there's many things you can do. You can change the stress path. Okay, where's the major principal stress, where's the minor principal stress, and you can change the drainage condition, undrained, fully drained. Okay, so there's many different tests you can come out. You can turn it into unconfined complexion test. It's not too reliable, but it's very fast, very low cost. It's a quick test, but result not too reliable. But it's quick, just help you to do a rough check. Okay. Usually in a triaxial test, we either do a CU test. CU, not Chinese U, it's consolidated undrained test. Consolidated undrained test with pore pressure measurement. Okay, so from that we can figure out CU, undrained cohesion intercept, undrained angle of friction, and then we also measure the pore pressure change. From that we can deduce the drained angle of friction and drained cohesion intercept and drained angle of friction. Okay, so it's very useful. Okay, so you can determine the undrained parameter. You can measure the pore pressure, and from that you can calculate the drained parameter. So it's a very good test. Okay, I think we will in next year we will learn to do the undrained, unconsolidated, consolidated undrained test. Okay. We can also do a consolidated drain test by allowing the drainage valve to open so that no pore pressure will generate. It's a very quick test. And then the result is C dash find dash. Okay, it's like a triaxial test. But by far, the most common one, most useful and common one is this one, triaxial test. Consolidated undrained test with pore pressure measurement. So it gives you C dash, C dash, C dash, C dash, C dash, find dash, and CU, fine U, and pore pressure change. Okay, so those are the most informative and also quite expensive. One test now, usually a commercial test, commercial lab will charge few $1,000s per test, somewhere from $3,000 to $5,000 per one test for one test. Okay, but usually in a site, you have to do at least something like at least 10, 20 tests. Okay, so on an average, they're charging you around $5,000 per test. So you can find out the cost of the triaxial test. Okay, triaxial drain test a little bit cheaper. It's around $3,000. Some lab only charge $2,000. Okay, but it only gives you that no information on the pore pressure change. Okay. Unconsolidated undrained test is a quick test. Usually, again, it's not too reliable. We may not do it. Okay. So by far the most reliable is the triaxial drain test or triaxial undrained test with pore pressure measurement. Okay. Now the concept of triaxial drain test. Okay, first talk about drain test. On the mention, we have a soil sample, cut it in a cylindrical strip, mount it in the triaxial cell, and then we allow first the water go in and completely submerge the entire specimen, and from that we apply the water pressure. The cell, or we call it the water pressure, and we call it cell pressure. The cell, because everything is mounted in a triaxial cell, so that we also call it cell pressure. This cell pressure is, or the confining pressure, there's so many names. Confining pressure, which is equal to cell pressure, which is equal to sigma 3. Okay, so initially, your soil specimen mounted in a triaxial cell, okay, and apply the confining stress. Okay, since this is a consolidated drain test, so we turn on the drainage valve as allow all excess pore pressure to drain out. Okay, so there's no pore water pressure. Pore water pressure is equal to 0. Okay, so initially sigma 1 is equal to sigma 3 equal to the cell pressure, and then after that we keep the cell pressure constant. Then we continues increasing the vertical stress. We call it vertical stress. Increase this one, but while keeping the sigma 3 constant, the cell pressure constant. The cell pressure constant, okay, and we just add the vertical stress through the vertical piston until the point we measure the development, okay, the vertical strain, the lateral strain, so we can plot the stress strain curve. Then we can find out when the soil start to fail. When the soil start to fail, you can see that that's roughly you can see that the failure plane start to develop across the soil sample. It's quite visible. You can see it, okay, because the cell, the triaxial cell, is made of plastic glass, clear plastic glass, and it's inside water, and then your soil sample is in the middle. So when you look into the triaxial cell, you can see the actual sample. Then when it fails, you can see this failure plane develop on the soil sample. Okay, and also everything is automated, recorded by the computer, so you can plot out the stressing curve and plot out all the response, and you know, oh, failure is developing, and then oh, you should stop the test because the soil failed. So it's quite easy if it's computer control. Okay, of course, the old generation everything was hand control. It will take you much more meeting. But fortunately, in our VTC lab, the triaxial test is fully computer controlled. Okay? Actually, the direct shear test, they have two sets of direct shear tests. One is fully manual control. One set is fully computer control. Okay, but for teaching purpose, we will use the fully manual control. Okay, but later, if you want to do your final year project or your teacher doing the research and things like that, or you want to in your geotechnical 3, they may demonstrate to you the direct shear test by computer control. It's much easier. But the triaxial test in IB now all change it to computer control. So we just set it up, press a free button, then computer do the work, and then we'll give you all the test data and then plot out the result for you, and then you can use it. Okay, but I think in your geotechnical 3, you still have to plot it by hand. Make sure you know how to do the calculation, even though you have the computer generate the result for you, but you still have to do it again by hand. Make sure you're able to get the same result as the computer, and plot it by hand. Make sure you know how to plot it. Okay. Wait for next year. Okay, from that, from the triaxial test, then again you will obtain the sample. Okay, and let me pick it. Okay, and in the triaxial test, the end result here is your major principal stress is here in the vertical direction. Your minor principal stress is in the horizontal direction. Okay, and then you also will see that the potential failure plane is making an angle theta from the horizontal. So angle theta can be related to angle of friction by this equation. Angle theta is equal to 45 degree plus find angle of friction divided by 2. Okay. Now, usually in triaxial test, we will not do only one test. We will do a series of tests, usually at least 3 tests. Each test we will use different confining pressure. We have, like, we prepared 3 soil specimens. Okay. Since we want to make it more precise, we want to find out the cohesion intercept and then the angle of friction more precise. So we will run usually the GEO requirement is at least 3 tests, each test with different confining pressure. Now this diagram only plotting result of 2 tests, because if you plot another more circle, then you can plot it here. Okay, another more circle. And if you do it correctly, the Mach Coulomb failure criteria will be tangential to here, to here, and to here. Okay, they're just tangent. Okay, just touching, not intersecting, not in this. This is the Mach Coulomb failure criteria. This line is the Mach Coulomb failure criteria. They should be just tangential to your Mohr circle. This is the half of the Mohr circle at the initial confining pressure. This is another half Mohr circle, a higher internal confining pressure, and this is the final Mohr circle at a higher internal confining pressure. Okay, initially sigma 1 is equal to sigma 3. It's just a point, but in the test we keep sigma 1 constant while increasing we keep sigma 3 constant. I'm sorry, sigma 3 equal to sigma 1 equal to confining pressure in the beginning here. But after that, we keep sigma 3, the confining pressure, constant. Okay, sigma 3 constant. It doesn't change. We only increase the vertical stress. Okay, so that means that we make the Mohr circle bigger, bigger, bigger until the point of charge failure. That means the Mohr circle just tangential to a Mohr-Coulomb failure criteria at this point. Okay, so first you get this result, and second we have another test. Okay, another test. So another test. Okay, now this time you have another specimen. Okay, we confine it to a higher confining pressure. Okay, this sigma in the second time the confining pressure is higher. Okay, confining pressure for the second test is higher than the confining pressure of the first test. Okay, so the initial Mohr circle is in here, just 1 point, and then after that we will increase the vertical stress while keeping the confining stress constant. So initially just 1 point, we increase the vertical stress, increase the vertical stress, increase the vertical stress. So the Mohr circle is keep expanding until another point of failure. This is sigma 1 at failure. This is sigma 3 at failure. Point of failure is just in here. Again, they are tangent to the Mohr-Coulomb failure criteria. From that, you can extend back to here. This is the center of your Mohr circle. Anyway, okay. So we have 2 points, but usually GO want us to do three tests, at least 3 tests. So now we want to do another one. Now here, the third specimen, similar soil. Okay, we trim from each soil, site investigation, from each layer of the soil, we take out a column of the soil specimen. From that, we trim at least 3 specimens for conducting at least 3 triaxial tests. One is at a lower confining pressure. The other one is higher confining pressure. The other one is even higher confining pressure. So confining pressure at C at the third time is quicker than the confining pressure in the second time, which is quicker than the confining pressure of the first time. So confining pressure at the first time, confining pressure at the second time, confining pressure first time, confining pressure at the second time, and maybe I changed it to white color. That's me. Now we have the confining stress at the third time. Okay, so initially we apply the confining stress. So confining stress, they're the same for the third time. So initially sigma 1 equal sigma 3. So sigma 1 equal sigma 3. So it's just a point. Right? Sigma 1 minus 3 is the shear stress. So no shear stress. It's a point. We keep sigma 3 constant while we increase sigma 1. So the Mohr circle extend. So it's way below the Moore Coulomb failure criteria, so the soil specimen is safe. We continuously increase the sigma 1. The Moore circle is increasing to here. Sigma 3 confining pressure remain constant, so it doesn't change in here. Okay, here. And then we continuously increase sigma 1, so the Moore circle expand to here. Okay, still safe, still below the Moore Coulomb failure criteria. And then we continuously increase sigma 1 until the point that the Moore circle just tangential to the Moore Coulomb failure criteria. Then the new failure point is in here. Now, if you do it correctly, all failure points A, B, and C should join as a straight line. Okay, so we plot a straight line tangential to point A, point B, and point C. Okay, then from here, from the y-intercept here, we measure the cohesion intercept. But in this example, it's just intercept as 0. This is a granular soil, so the cohesion intercept is equal to 0. But if this is a clay soil, is cohesive soil, then this cohesion intercept here is not 0. It should be higher with some value of cohesion intercept. Okay, but it's just in this example, it's a granular soil, it's a sandy soil, so cohesion intercept equal to 0. And then in here, we measure the angle. This is your angle of friction. Okay, so angle of friction here, cohesion intercept here. So that is the 2 parameter that we need to determine. Okay, that's how. Of course, here is we just talk about the theory, maybe a little bit for you to understand. But then when you actually do the test, it will be much easier. But the concept of the triaxial test is like that. But the concept of direct shear test is similar. But if we're able to measure, if in the triaxial test we have the pore pressure transducer. If we're doing a CU test, consolidated engineering test with pore pressure measurement, then we will measure the excess pore pressure we generate. Okay, so initially we can plot the total stress Moore circle. Okay, with the total stress Moore circle, effective stress is equal to total stress minus pore pressure. Okay, so in a triaxial test with pore pressure measurement, we measure the total stress, total confining stress, sigma 3 total, and total vertical stress, sigma 1 total. So we can plot out the total stress Moore circle. Okay, this is the total stress. Moore circle. Now again, we will do it at different confining pressure. Say, we just show you 2 in here. Otherwise, the figure will be very busy. It's difficult to see. Okay. Say we have initial total stress Moore circle with lower sigma 3. This is lower. And then second time we increase the sigma 3 confining stress, we take another soil sample. See, from the same investigation, from the same column of soil, we trim one sample, apply a lower confining pressure, get the initial Mohs circle, initial total stress Mohs circle, and then from the same investigation, we take another soil sample from the same drilling on the same soil profile, but just a little bit lower. We trim another soil sample, put in the triaxial test, and apply a higher confining stress, initial confining stress here, and conducting a consolidated undrained test, making a higher, larger confining stress, so a larger Mohs circle. Now from this tangential point and this tangential point, we can join it with a straight line. But since here we are plotting total stress, so the cohesion intercept and the angle of friction is under undrained condition. So this cohesion intercept is undrained, Cu, cohesion intercept under undrained condition. This is an angle of friction under undrained condition. Find U, okay? Cu and find U. Cohesion intercept under undrained condition, U. Angle of friction under undrained condition, find U, okay? If we have the pore pressure measurement, then the Mohs circle we can subtract minus the pore pressure. Then we can obtain the effective stress, okay? Total sigma 1 minus pore pressure, the effective sigma 1. Total sigma 3 minus pore pressure. Pore pressure is the same. Effective sigma 3. So from effective sigma 3, plot it into effective sigma 1. Now maybe I erase that. Okay. Now initially this is total stress, sigma 1 total, minus the pore pressure, return into effective dash, right? Sigma 1. This is pore pressure. Initially, sigma 3 is here, minus the pore pressure we measure. Then this means for this Mohs circle, this is effective sigma 3. Okay, so this we plot sigma 3 effective to sigma 1 effective. This is the effective stress Mohs circle. While this is the total stress Mohs circle. Okay, if I draw a straight line tangential to the total stress Mohs circle, then this is the total stress failure criteria, failure envelope. Okay, so here is the cohesion intercept, but in this example it's just hitting zero. It still stands for granular soil, but For cohesive soil, then they will have a cohesion intercept. Cu in here, and then this is phi u. Angle friction under undrained condition. Cohesion intercept under undrained condition. If we plot it in effective stress Mohr circle, which is here, then we find another tangential line, tangential to the effective stress Mohr circle, the purple color. So this is the effective stress failure envelope. Effective stress failure envelope. Okay, so from here we find C dash, but it happened to be against zero. But then, believe me, if for cohesive soil, then C dash is not zero, and then this angle is phi dash. Okay, angle friction under drained condition. So usually, not usually, it must be condition. Effective angle of friction will be larger than the angle friction under undrained condition. Okay. Now, if you don't find this condition, then your answer would be wrong. Okay. Angle friction under drain condition, effective angle friction must be larger than undrained angle friction. Okay. This notes didn't talk about it, but if you read the textbook, maybe some textbook mention about it. If you don't get this condition right, that means your test must have some mistake somewhere. Okay. Theoretically, angle of friction under drain condition must be larger than angle of friction under undrained condition, because if you have water, okay, lubricating the soil particle, the friction must be low. If you don't have water lubricating the frictional interface of the soil particle, the friction must be high, right? As simple as that. So the result reflect that, okay? But just remember that, okay? Now, if we have to do it, a so-called unconsolidated undrained test, UU test, that means initially we don't do a consolidation, just apply the load. Doesn't matter what confining pressure, then you will get all the Mohr circle the same size. And then angle friction would be zero. And you just have a cohesion intercept. Now this is totally only working for short-term condition. Undrained condition. That means that in the foundation, for some reason, our load apply into the foundation very quickly. Within 1 hour, all the load apply into it. Then we have to assume that. But in foundation, you can imagine the construction of building usually take months to years. So it is almost impossible for you to have this short-term undrained condition in a foundation situation, right? But for slope stability, like a couple of days ago, we have yellow wing and suddenly turned into red wing, and the whole light is full of wing. Okay, so rainwater can suddenly come in and saturating the soil. Okay, saturating the soil slope, saturating the soil foundation. So within a couple of hours, all the soil is fully saturated by rainwater. But it doesn't have, maybe the soil is have low coefficient of permeability. So the pore pressure is difficult to dissipate. So in that situation, then it would likely for the slope to fail under undrained condition, or the foundation to fail under undrained condition. So in this situation, then we have this so-called short-term undrained condition failure. Okay, now when we go to the last chapter, the bearing capacity, and then the second last chapter, the slope stability, we will examine the slope under drained condition, fully drained condition, and the slope and foundation under fully undrained condition. Then we will examine which case is more critical, give you a lower factor of safety, more easy to fail. Okay, so usually in geotechnical, we will test both cases, short-term undrained condition and long-term drained condition. Because we don't know which case is more dominant, more important. So we have to do a series of calculations. One is for short term, one is for long term, and then we compare that, and then compare which one is more critical, easy to fail, lower factor of safety, and then we pick that as a design case, as a dictate case, okay? Because it's more difficult, critical, it's more easy to got failure, okay? So it become more of our engineering attention, okay? Because it's more prone to engineering failure. So in all the geotechnical works, we have to find out both undrained condition, getting the undrained soil parameter, and also doing the drained condition, getting the drained soil parameter, and then from that we test both. Okay, later in chapter 4 and chapter 5, when we're talking about slope stability and bearing capacity, we will test both conditions, both drained condition and undrained condition. Then you will realize the importance of doing the right test. Okay, I cannot tell you all drained condition is less critical than undrained condition. It's not always the case. Okay, we have to test all the different possibility and find out which one is more critical. Okay, and then pick the more critical one as our design condition. Okay, so we have to do a lumbar testing. Okay, so that is part of the geotechnical engineering routine. Okay, this is the unconsolidated undrained test. Again, it just fit it back to this is under undrained condition, undrained, totally undrained condition. Okay, so absolutely no consolidation, no drainage of water, unconsolidated. Soil is not consolidated, so there's no change in void ratio, and then this test under undrained condition, we call it UU test. Okay, so this will always give you angle friction yield 0, and then only give you the undrained cohesion. This usually represent the most critical condition for slope, at least. This usually more critical, give you a lower factor of safety, dictating the short-term failure condition. Okay, but not all the time, but most of the case for slope stability problem is this unconsolidated undrained condition would become dictating condition. Okay, but anyway, when we go to chapter 4, we will go through different phenomena. Then you will realize what is it under drain condition, what is it under undrained condition. Okay, so this is just talk about one of the special undrained test is called unconfined compaction test, but it's not very reliable, so you can follow, almost forget it. Okay, so another thing that we are talking about is if we have the soil is remolded, disturbed, then it will disturb the soil fabric. Okay, remember the soil fabric, you have clay and silt and sand particle. Due to the geological formation, it has certain internal structure. Now, every time we take the soil sample out from site investigation, our drilling, our sampling procedure, we're taking out away from the ground, we bring it to the lab and mount it in the triaxial apparatus. All this will cause the soil to remold. Remold doesn't mean we disturb to a certain degree, certain disturbance to the fabric of the soil. Okay, so it will change the structuring response. Practically, it's impossible to obtain a totally undisturbed soil sample. Okay, in our sampling technique, no matter how careful you are, it always induces some degree of disturbance to the soil fabric. Okay, but because of that, like as a geotechnical engineer, when we supervise the worker working in the construction site to take the sample, we know that the soil, once it's disturbed, the soil fabric will change. It doesn't represent the true condition of the soil happening in the field, in situ, in the field condition. But when we design a structure, a slope, a road, a building on the soil, everything is built on top of the existing soil. So we are working on the undisturbed soil, okay, instead of the remote soil. The remote soil may be disturbed during the sampling process. Sampling, handling, testing process will change the structuring response. Okay, reduce the ultimate strength of the material, reduce the initial stiffness of the soil. So it doesn't truly reflect the actual soil behavior, which is not good. Okay, so as a geotechnical engineer, we have to try to be very careful and inform and supervise our site staff when take the sample from the ground. Be very, very careful not to disturb, try to reduce the amount of disturbance. And we trying to take a sample as close to the in situ condition, the existing condition of the soil in the ground at site as possible. Okay, because disturbance, remolding will significantly destroy the soil fabric and therefore change the structuring response, change the shear strength of the soil, change the initial stiffness of the soil. Okay, so it's very important for us to do undisturbed sampling. Okay, instead of getting too remote the soil, we want undisturbed soil. Okay, so here show you a sample. This is after the testing. This is the failure plane you see after the triaxial test. This is the failure plane you see after the triaxial test. This is similar test. This is on the undisturbed sample. So you clearly see the failure plane very clearly. Okay, but this is a slightly disturbed soil, but that during sampling, handling, testing, there's some remolding going on, so disturb the initial fabric. So you can see that the failure plane is not so visible, and the structuring failure mode is also changed. So it just indicate to you disturbance due to sampling have a significant effect on your result. But as a geotechnical engineer, we want to take a sample as close as much as possible to the in situ condition we find in the ground as possible. Okay, otherwise our result will not be accurate. Okay, so I think this is the end of my talk today. Okay, it's 5 o'clock. Okay, so I will be stopping here, but just remind you once again, next week because it's a中秋节, okay? So we don't have class, okay? So I encourage you to study the notes, and also I already sent out the tutorial question and answer. You can take a look, okay? So the week following, like at the coming long weekend, and then 2 weeks later, we will have a face-to-face class, okay? So please check your the value or where is the face to clean. I don't know. I forgot to check it yet. One of the classroom. Okay. Okay. I forgot which one. But anyway, make sure you check it. And then next lecture, we will have a face-to-face lecture. Hopefully the pandemic is under control, and then we can finish our face-to-face class for the remaining 6 lectures. Okay, I should have 6 more lectures with you. Okay, so from that point, I'm dropping here, and everybody have a happy Mid-Autumn Festival. OK， 咁啊平平安全全 ，OK， 咁啊開開心心過節 ，OK， 齊上齊落，咁啊到依家係咁多先 ，OK， 我哋講聲拜拜 ，OK， 拜拜，5點鐘，拜拜。